welcome to Unit 1, Lesson 3, Combining Transformations. So up until today, we've looked at how to vertically and horizontally move functions. And then previously we looked at how to stretch and reflect functions. And now we're going to work on combining all of those things together. So when we have a transformation that's going to be applied to a function, we can do many of them within the same function, but there's an order of operations that has to happen. Just like bed mass, we have an order of operations that applies to our transformations. So it says here, multiple transformations can be applied to a function using the general transformation model y equals af b x times h x minus h plus k. To accurately sketch the graph of a function in this form, the stretches and reflections a and b should occur before the translations h and k. Okay, so at the top there's a little chart describing that process. So you're doing your h and your k as your last moves. The a and the b will come first, but it doesn't typically matter which order you do them in. So for example, we have this graph here, f of x, and we've done some things to that graph to do the transformations to it. So our formula for g of x is negative 2 f 1/3 x plus b plus 8 minus 3. So our transformations are a reflection from the axis of x, and I just have the choices here for you guys so that you can pick which one if you're working ahead of me, but x is the correct answer. Okay, so we flipped it over that x-axis. Then a vertical stretch by a factor of 2. Here is our 2, that's our a value. A stretch horizontally by a factor of 3. So here is our b value. Remember, when it's 1/3, we're going to multiply all x values by 3. And then now that we've done our stretches and reflections, we're going to be able to make our translations. So we move it 8 units to the left. Here's our h value for horizontal movement, and a vertical translation down by 3 units. Now the resulting graph that you end up getting looks like this g of x. It continues off the graph, but of course it's a parabola. It goes on indefinitely. And when we write out the corresponding equation for that, all we've done is just take the f out of there and write down all the changes that we're making to that original function. Negative 2 stretch, 1/3 stretch, move left 8, and down 3. So this example just breaks it down into steps, showing exactly what's happening to the function f of x equals x squared. So for us to get to this function here, negative 1/2 f 2 times x minus 4 plus 1, what we're doing is we're using mapping points in this situation to see how x and y change. So we're going to start with the horizontal stretch about the y-axis by a factor of 1/2. So we're going this way across the y-axis. Now, if you notice, the points have changed. They've gone from negative 2, 4 to negative 1, 4. Okay. When we look at our mapping points, we can see that x and y, our original, are now 1/2 x, which makes sense because we have that 2 affecting our x values, and y, our y's have not changed. Okay, notice that this new mapping coordinate becomes our starting point down here. So this mapping coordinate is our starting point. Now we're going to see what's the next change we're going to make to this graph. Okay, then the second part is a vertical stretch about the x-axis by a factor of 1/2. So we're looking at that a value now. And remember, the a value affects our y values. We're going to multiply all of them by 1/2. So you can see here in this mapping image point, we have negative 1, 4 it changes to -1, 2. And our general format for our mapping coordinates, this 1/2 x, nothing's changed. We're leaving it alone and moving it over here. And then all of our y values are being multiplied by 1/2, which is our value of a. Okay, keep in mind again that this now becomes our starting point for the next step that we're doing. Thirdly, now we can look at that reflection, that negative value here, and that will help us decide what to do with the parabola. So we have this parabola now, the blue line, and we have a negative value on that a. So in our mapping points, what's going to happen? We still have that 1/2 x, that hasn't changed. And then we know that this negative value affects our y values. So we're just going to apply that negative value here to the y's, and that will help us to flip our parabola upside down. The last thing that we're going to do is look at our horizontal and vertical translations, and we can do that at the same time. So if you notice in your original equation, keep in mind this becomes our starting mapping point. So we're just adding on to the values each time, step by step. Now we're going to do a translation of 4 units to the right and 1 unit up. So notice what happens to the x values. Remember, h is what affects the x values. Our 1/2 x, it's now going to be 1/2 x plus 4. And then we shift up every y unit by 1. So our y values are now -1/2 y plus 1. So this gives us our coordinates to use for any point on this graph. When we start with f of x, we can pick any point that's on there and apply these changes to it, and we'll get this resulting g of x graph with the shifts in it. Now, in our general formula, we would see that a is equal to 1/2, b is equal to 2, h is equal to 4, and k is equal to 1 to produce for us that g of x formula that's come from doing all those translations. So instead of doing each step, we can use the matching rule to find the image points to trace a transformation. So it says here, describe the combination of transformations applied to the function y equals f of x to obtain the transformation y equals 1/3 f 2x. Draw the graph and show each step. So I just wanted to remind you that this is our a, 1/3, and our b value is 2. So we have this original graph here. I'll just bring those values down. A equals 1/3, b equals 2. So this tells us that the graph was stretched horizontally by a factor of 1/2 and stretched vertically by a factor of 1/3. When we look at what's happening to our xy coordinates, we're going from our original just standard xy, and then we're applying the b value here and the a value here. So for any coordinate on our graph, we can just use this general matching point formula, x over 2, 1/3 y, on any coordinate that's available. So if we take our coordinates that are plotted on the graph, nice and easy, 0, 0, of course, is an invariant point. It's not going to change. In point B, you're just going to go 1 divided by 2, give you 1/2, and 1 divided by 3 to give you 1/3. In C, it goes to 2 2/3. In D, I left it in fraction form here. It's 9 over 2, but just keep in mind that that is the same as 4.5, 1. So what we can see is that nice change in our graph. It's shrunk in size by half, and it's also shrunk in size vertically by 1/3. It's 1/3 as tall as it used to be. This second example here, we're going to be using the same graph, but I wanted to point something out to you so that you don't make this mistake on any of your assessments. Now, we have this general formula, y is equal to AF B x minus h plus k, all right? And in our formula that we're given here, we have f times 2x minus 6. But the problem with that is we can't clearly see the value of b. So what we need to do is get this 2 out of here, and how we do that is by dividing both terms by 2. So 2x divided by 2, that just leaves us x. And then -6 divided by 2 leaves us -3. That 2 comes outside the bracket to show that we're still multiplying by it. And now that we've done this, we can clearly see that our b and h values are 2 and 3. If you're not sure what this symbol means, that's a shorthand symbol for therefore. So working with this graph, f of 2x minus 3, we're going to start with the same original points. So I'm just going to move the formula down here. Now, we're going to apply the b value, to our x coordinates. So b is 2 here, it's greater than 1. So you divide all x coordinates by that number. So we get x over 2 for our general format. Then the second part of this problem that affects the x coordinates is the fact that we have a horizontal shift here of -3. So that -3 gets applied to the x coordinates as well, and we have +3 because it's x minus h, so the value of this is actually positive. Our y coordinates, nothing changes. So you can see here the shape of the graph changes in the x values, but the y values, the height of the graph, doesn't change. So the exact same thing you did last time, you're just plugging in this value. In this one, there's a shift horizontally 3 units. So this 0a value, it won't be an invariant point in this example because we're going 0 divided by 2 and then adding 3 onto it to give us this x value. Notice that your y values do not change, 0, 1, 2, and 3. Now, another type of problem that you could get is to determine the point of g of x if g of x equals -3f, brackets 2x plus 6 plus 4, and the point of f of x is 4, 16. So just like in the example above, you want to take that factor of 2 out from the brackets so that we can clearly see the value of b and clearly see the value of h for our charting. So we have some terms here. Our a is equal to -3, our b is equal to 2, h is equal to -3, telling us to move left, and k is equal to +4, telling us to move up. Now, with our general points, here's what's going to happen. b and h are applied to the x values. So remember, b is greater than 1, we're going to divide by the value of b. So x over 2, and then the horizontal shift, -3. And then for our y values, a and k are going to affect it. So we're going to multiply all y values by -3, and then shift them up 4 units. So if we're given the point 4, 16 on the graph, all we do is plug these values into our general matching points and get the resulting coordinates, -1, -44. So here you just went 4 divided by 2, which is 2, -3, -1, and -3 times 16, -48, +4, -44. Our last thing that we need to do for this topic is to be able to write the equation of a transform function graph. Now, we have the function f of x here shown, and some things happen to it, and this is our new function g of x. So to determine the formula, we want to use this general format, af b x minus h plus k. And to do that, what we can do is look at some key points on our original graph. So on our original graph, we have -4, 4, 0, 0, and 4, 4. Now the point 0, 0 in the graph is not affected by any stretch, horizontal or vertical. Okay, so A and B values don't matter, and that makes it a really good point to look at because we know that the only thing that can happen is it moving up or down. So if we look at the coordinates that came out of the transformation, we can see that 0, 0 has moved 7 units to the left and up 2 units. Okay, 7 to the left, -7, and 2 units. So we now have our h and k values. H is -7 and k is +2. There's no reflection, and you can tell that because it's not changed directions. Now, in the second part, we need to figure out A and B. And what we want to do is compare how have the distances between points changed. So if we look first at the y values, in f of x it's 4 units, and in g of x it's 8 units. So we can see that the height, or A, has doubled by a factor of 2. So we have A equals 2. Now, for the x values, to find our B, we have 8 units in our original graph and 2 units in our new g of x. 8 divided by 2 gives us a factor change of 4. So once we have these 4 numbers, h, k, a, and b, the problem becomes very simple. All you have to do is just plug them into our general formula, and your resulting formula will be g of x is equal to 2 times f times 4 x plus 7 plus 2. Beyond this, you have some practice questions based on the examples that were provided in the notes today. You can go ahead and complete those.